Hi everyone, I'm Alex Pry. My supervisors are Lewis Mitchell and Simon Lucy, the Director of AIML. And I'd also like to thank Hemanth, who is a researcher at AIML, who's helped out with this project as well. And he's in chat. So my maths honours project talk is on deep learning, Shannon interpolation, and what lies between. When you hear deep learning, you might think of, say, an image classification task where you're training a network on thousands of images. Well, forget about that, because we are training neural networks on just a single image at a time. So at the top here, we have an image that is 128 by 128 pixels. And our aim is to, instead of storing all those pixels individually, represent that as a continuous function that takes as input a two-dimensional coordinate, so a row and column on the image, and spits out the value or the color at that coordinate. And so we do that using something called a coordinate network, because it acts on coordinates. At the bottom, we have two approximations to that image. The reason they are not so good is because we're also compressing the image. And instead of storing those 16,000-ish pixels, the methods we're using on the bottom only use about 1,000 fragments to store the entire image. On the bottom left, we have Shannon interpolation. And on the bottom right, we have a coordinate network. By the end of the talk, you'll know how I created these and what these expressions down the bottom mean and what the links are between these two interpolation methods. I'll start by just talking about classical interpolation, Shannon interpolation in particular, and then how you can generalize that slightly. Then I'll talk about neural network basics, and then coordinate networks, which is how you use neural networks for this interpolation problem. And then finally, I'll kind of compare the two methods, pointing out some of the similarities between them, and go back to those experimental results and try to explain parts of it. All right, firstly, Shannon's results. So the general setup is we have some signal, such as a radio signal, that we represent as a function f, and we are sampling it every t seconds. And we want to take those samples and reconstruct the original signal. And we also want to know, what should t be? How often do we need to sample it? So the Whittaker-Shannon interpolation formula is given by this here. F hat of x equals the weighted sum of many copies of a sinc function that are shifted by different amounts. If you haven't seen the sinc function before, this is the formula for it. It's sine pi x divided by pi x with a discontinuity fixed up. So the Nyquist-Shannon sampling theorem says that if our original signal is band limited with no frequencies higher than b hertz, and we sample at the Nyquist rate, in other words, we want t to be less than or equal to 1 over 2b, then our reconstruction using the Shannon interpolation formula will be a perfect copy of the original signal, which is pretty nice and a pretty strong result. As you saw earlier, we're dealing with images though. That's two-dimensional instead of one-dimensional. But it turns out you can generalize Shannon interpolation, and similarly strong results apply for multi-dimensional signals as well. So for interpolation in general, we have a signal. We no longer assume that it's one-dimensional. It can have multiple dimensions. So the number of dimensions is d. The samples can be limited, bounded in terms of how many we take, and the signal doesn't necessarily involve time. So with our image, our two dimensions are spatial dimensions. Our samples, we can split our samples up into a matrix X containing all the sample coordinates, and then a vector y containing all the sample values at those particular coordinates. With classical interpolation, a common approach to signal reconstruction is we try to create our reconstruction f hat of x by taking a weighted sum of a linear combination of some basis functions. So little phi I here can be any basis function. In Shannon interpolation, we use sinc, but you can use other functions as your basis functions. And a common thing to do is to just have one function and then you just shift it different amounts for the different basis functions. So similar to with Shannon interpolation. Our coefficients, Wi, well, Shannon interpolation gives one way to know what those are, but we can solve it more generally to work out what those coefficients should be. Our aim is that for our reconstruction f hat to be as close to the original signal f as possible. We only really have access to the sample data though, so at the very least we want our reconstruction to go through those sample points. So we can solve this exactly in some cases. So we want y equals f hat of x. So in other words, it goes exactly through the sample points. All our coefficients, wi, we can group them up into a vector, w. And instead of applying the basis functions individually, we can group them up into this big phi of x, which gives a matrix that is every basis function applied to every sample coordinate. And so you end up at the bottom here with just a linear equation where you've got a known vector times an unknown vector, a known vector that equals an unknown vector times a known matrix. And we can solve that so long as that matrix is invertible. So in particular, we want the matrix to be square. So that means the number of samples that we take and the number of basis functions that we have to be equal. We want the matrix to be full rank. And a sufficient condition to ensure this is if all our basis functions together form an orthogonal basis of the function space that they span, then that's enough to guarantee that we can solve this exactly. But if we can't solve it exactly, we can at least approximate things. So now, instead of trying to go through all the sample points exactly, we want to at least minimize the distance to the sample points. And so that's what, y minus f hat of x is the distance to those sample values. And we take the mean squared error or equivalently the L2 distance, and we try to minimize that. So on the third line here, w hat equals argmin. We've rewritten this minimization problem in terms of those matrices and vectors that we have. And so that is just a linear regression problem. So we can apply at least squares method or some other method for solving it to find what our weights w hat should be, and then we use that to create our reconstructed signal f hat. So you can do this using sinc interpolation. So Shannon interpolation. So you no longer use that Shannon's interpolation formula, but instead you can solve it this way. But what's more common in practice is passing a signal through an anti-aliasing filter, which is an ideal low-pass filter, ideally, and then applying the Shannon interpolation formula after that. And that will give you approximate interpolation, but it turns out that is actually equivalent to this and will give you the same result. So we can express it this way with this formula, and it's still talking about that kind of best case interpolation with Shannon interpolation. Finally, the kind of more general form of this, if say we're not using a linear combination of basis functions, but we've just got some interpolation method. Well, there's an associated function space of all the functions you can possibly create. And so the general problem is finding the argmin to find the particular function in that function space that is as close to the sample points as possible, and then use that as our reconstruction. Just give me a sec. Yeah, so that's interpolation. Let's move on to neural networks. Even if you haven't worked with neural networks much, you've probably seen a diagram that looks a bit like this. The nodes are neurons. They are arranged into layers. We've got an input layer, an output layer, and here we've got two hidden layers. Data flows strictly left to right, so it's a feed-forward neural network. Each neuron is connected to every neuron on the next layer, so it's a fully connected network. The way the neurons process data is they take all the input signals they have, they take a linear combination of those, and then apply a nonlinear activation function to the result. Typically, value is commonly used. Okay. But we don't need to think of it in terms of this diagram and think about individual neurons. Since we have some mathematical background, we can express it much more succinctly by using vectors and matrices. So each layer we can just treat as one big vector containing all those neurons. And the connections between layers we can is basically matrix multiplication, because it's just taking these linear combinations for each component of the vector. And then our activation function, we can just say that it acts component-wise on each component of a vector. And so overall, we can write a formula for the neural network's behavior like this. So working backwards, X is the inputs, then it's multiplied by some matrix, and then we apply an activation function, and then we do that a few more times, depending on how many layers we have, to finally get a value out. So that's a static neural network, but of course, the other half of neural networks is we need to train them to do response. So W here, I've just written W, which is actually grouping together three matrices, W1, W2, W3. These are matrices of weights, and these are all parameters that we can change. So what we do is we feed in our training data, observe what the output is, compare it to what we want the output to be, and then use that distance, that error, and then feed that into an optimization algorithm such as gradient descent that will then change those weights in the matrices in order to iteratively get closer and closer to the behavior that we want from the function. So I won't go into the details of those algorithms, but overall, you can think of it as it's trying to solve this argmin problem down the bottom here. So it's trying to find the weights in the matrices that will minimize the distance to the training data that we have. So that's starting to look pretty similar to our interpolation problem. How do we apply this to a low-dimensional task, like interpolating on an image? Well, our inputs, the inputs will be those sample coordinates, and the outputs will be the sample values, or the reconstructed sample values. So yeah, we just use it as is to find, to do gradient descent to find those weights, and then finally we have a static neural network that reconstructs that signal. But this doesn't work great. The big issue is something called spectral bias. This setup will tend to learn the low frequency aspects of the signal quite quickly, but the high frequency components of the signal, it will learn slowly or not at all. But we can find ways around that. So this has two inputs, say the X and Y, or the row and column. from an image. Instead, we can have a larger number of inputs. So instead of feeding our coordinate vector in directly, we feed it through some basis functions, component-wise. And here I've written it using big phi, and that's no coincidence because we use the same sorts of basis functions that you use for classical interpolation. So you can, for example, use many copies of the sinc function shifted by different amounts. And then the outputs of those basis functions are then treated as the inputs to our neural network, and then the rest of it works the same as before. So in terms of equations, this is almost exactly the same as the previous slide, but instead of feeding in x directly, we feed in big phi of x. So we're doing this extra pre-processing step. And the result works pretty well. Oh, one thing I should mention is we still kind of have some architectural choices to make here. Pictured, we have 2 hidden layers, but we can choose to have more hidden layers or less hidden layers. And in fact, if we just drop those 2 hidden layers and have 0 hidden layers, then we'll have these basis function outputs fed straight into the output of the neural network. And the neural network will still try to choose weights to associate with those. So what you end up with is just a linear combination of those basis functions, and it turns out to be the same as classical interpolation. So in a sense, you can do classical interpolation using a neural network, except it will be a single layer perceptron, so technically not even a neural network anymore, because it has 0 hidden layers. So moving on to how do we compare our interpolation methods? Well, each of these methods will do better as we allow it to have more parameters, until eventually, if you have too many parameters, it might start overfitting. So to compare them fairly, we need to limit the amount of trainable parameters or coefficients that the model is allowed to use. So we need to count how many parameters are there. For Shannon interpolation, if we have d dimensions and we have n basis functions per dimension, then the total number of parameters or coefficients for those basis functions will be n to the power of d. I haven't gone into the reason why, but just trust me for now. Whereas if we use a coordinate network, we've got some extra variables. We've got h, the number of hidden layers we have. We need to choose how wide our hidden layers are. And we can just express that as a ratio of how wide are the hidden layers compared to the input layer. And long story short, you get a parameter count that looks something like this. It's not nearly as short. But something to note here is how do each of these depend on the number of dimensions? So P for Shannon is exponential in the number of dimensions. And for a coordinate network, it's only quadratic in the number of dimensions. So if we graph that, here the x-axis is the number of dimensions, the y-axis is the log of the number of parameters, the black diagonal line is parameter count for Shannon interpolation or classical interpolation, whereas the green line is the parameter count for a coordinate network with some particular architectural choices. And the interesting thing is that as we get higher and higher dimensionality in our signal, classical interpolation gets really expensive really fast in terms of number of parameters, whereas a coordinate network, the number of parameters still increases, but not nearly as quickly. So this doesn't tell us anything about performance. This is just telling us about number of parameters, but it still maybe gives us a bit of a hint as to why neural networks are so good for high dimensional data, because at the very least, they can be implemented cheaply in terms of the number of parameters you need. Anyway, going back to my experimental results, the bottom left and bottom right are the same as that first slide. So we've got on the top, we've got the original image. Bottom left is Shannon interpolation. Bottom right is a 6-layer coordinate network. And then in between, we've also got a 2-layer and a 4-layer coordinate network. So you can see from eyeballing it that adding more layers, so adding deepness, seems to help give you a better approximation. And we've also got the mean squared error down the bottom here. So we can confirm numerically that as we add more layers, our approximation gets better. So what's the deal with this? We've got these strong results about Shannon and how great Shannon interpolation is. Well, part of a consequence of those results is we know the function space of Shannon interpolation quite well. The functions it can produce are the set of band-limited functions for a particular band limit. The function space for neural networks is not as well understood, although there are some results like the universal approximation theorem. But neither function space strictly contains the other, so we can't simply say that one's better than the other. But what's kind of more relevant is how do they work on real-world signals? And it's been shown that natural images, such as from photography, are not band limited. So that kind of suggests that Shannon interpolation just really isn't the right tool for this. Whereas just from experimental results, it seems like coordinate networks do a pretty good job of taking advantage of redundancies in the image and being able to approximate them and compress them fairly well. Just a sec. All right, so overall, I talked about a general way to express the interpolation problem. Talked about how Shannon's interpolation, you've got a vector of weights times a matrix of big phi of x from some basis functions. Neural nets, you feed in your weights and your coordinates straight into a neural network, whereas with coordinate networks, you feed in your weights, but you embed your coordinates by running through this basis function. And so the fact that it's using a similar basis function, it means that it's kind of close to Shannon interpolation in some ways. In terms of total number of parameters, coordinate networks require less parameters, usually, in many cases at least. And we've got the experimental result that a coordinate network can do an order of magnitude better than Shannon interpolation, at least for interpolating on this particular image. One more thing, coordinate networks are still an active area of research. AIML has published several papers related to it. And even though I've talked about images and interpolation for this talk, you can use them for a much wider variety of tasks. So for example, use them to represent three-dimensional MRI data, or 3D objects, videos, and so on. So there's more to it than I maybe suggested by this talk. Yeah, that's it. Thanks for listening.